data. So what we did here is we took, it looked like we had two samples, but really we had paired data. So we had data from two sets of values from like one individual or one object. So we defined something new called mu-D. So here's an example about caffeine withdrawal. So they looked at a caffeine deprivation study. So 1 to 2 day period, the subjects took capsules containing their normal caffeine intake. Another 2 day period, they took placebo capsules, and they randomized which order they took it. And then they took the difference in their depression ratings by doing placebo minus the caffeine. And they want to know whether being deprived of caffeine would lead to an increase in depression. So remember when we talked about paired differences, we use that mu-D, and generally we always set it equal to 0. You don't have to set it equal to 0. That's just the easiest case, and that's usually what we did in class. And then they wanted to know if the placebo minus that caffeine is greater than 0. So, and they're just stating what the parameter is, and since the no significance level is given, we're going to use alpha equal 0.05, so you can pick one. The reason why we know it's greater is because they think that being deprived of caffeine would lead to an increase in depression. So, and in this case, the lower the score, I guess, the more depressed you are. Alright, so then to go through the conditions again, the random condition is met. They looked at a graph. And they're just saying here there's no outliers or strong skewness, so they think that the T procedure will be okay. It says that there are not sampling, so it isn't necessary to check the 10% condition. I think you would be okay if you checked the 10% condition here, though. They found the mean and standard deviation, so what I would have you do is I would have had you type in these values into like list 1, these values in list 2, and then do list 2 minus list 1, and then you could use the data option from the t-test. If you use the data option, you would have gotten that. Then you can use the t-CDF, or the t-test would have also given you the p-value, so there's the p-value. So then the p-value is much smaller than our chosen significance level, we reject the null. And we can conclude that depriving caffeine subjects of caffeine caused an increase in depression scores. Just realizing just some things about using tests wisely. So one thing we talked about is statistical significance versus practical importance. So sometimes there was like an example in the book about a scab falling off a half a day earlier, and so the scab it was statistically significant that it fell off a half day earlier, but really who cares that your scab falls off a half day earlier. Another thing was don't ignore lack of significance. So the thing about not ignoring it is that sometimes it's just useful information to even know that things are not significant. Statistical inference is not valid for all data sets. So this is like kind of the garbage in, garbage out. So if you collected your data poorly, then there's no point in doing statistical inference on it. Beware of multiple analysis. So don't keep repeating something over and over. Don't keep running the same test over and over again. At some point you are going to find what you're looking for. So let's say, your first test is fail to reject. You do another one, it's fail to reject, and you keep doing this over and over and over again. And finally, 1 out of 20 of the test tells you to reject. Well, yeah, at some point you are going to get a test that's going to tell you to reject, because there is those samples out there that give you the type 1 errors. And here's the summary for the whole section about means. And that's it.